now is one of our longest-running research projects. Our team at Microsoft has been able to take a subatomic particle that has only been theorized until now.
Inside Microsoft's highly secured facility, scientists were developing a machine that could transform the future of technology. Hidden behind strict security measures, they worked on advanced quantum computers designed to solve problems far beyond normal human capability. But suddenly, the entire project was shut down without any warning or public explanation. Rumors quickly spread about failed experiments, strange discoveries, and unsettling results that may have pushed the project into dangerous territory. Some believe Microsoft uncovered a breakthrough too powerful to manage, while others fear they discovered flaws in quantum systems that could threaten modern technology itself. The billion-dollar quantum gamble. Computing changed the modern world by turning information into tiny electrical choices. Every message, photo, payment, and search depended on machines that processed data through binary code. Traditional computers used bits, where each bit existed only as 0 or 1. This simple system powered phones, laptops, satellites, and financial systems with astonishing speed. For daily tasks, this design handled billions of operations quickly, making modern life possible through precise streams of digital decisions. Classical machines attacked problems through structured calculation. They tested possibilities one after another or divided workloads across many processors. This approach worked brilliantly for browsing, gaming, banking, and engineering. Yet certain challenges became so much that even advanced supercomputers struggled. Some calculations involved such massive numbers of variables that processing every possible answer would take millions, billions, or even trillions of years beyond practical reality. Breaking advanced security systems required testing unimaginable possibilities. Predicting molecular behavior for medicine demanded tracking endless atomic interactions. Designing efficient shipping routes across the world involved endless variables shifting constantly. Climate prediction pushed complexity even further by requiring massive particle-level simulations. In these situations, ordinary machines reached a wall because brute force processing alone couldn't reasonably cross such mathematical mountains. Quantum computing emerged from this barrier by using the strange laws of subatomic physics instead of standard electrical logic. Rather than bits, these machines relied on qubits. A qubit behaved unlike anything in ordinary computing because it could represent more than a single fixed state. This radical shift created a new framework where information itself operated according to the bizarre behavior of quantum mechanics. One essential principle was superposition. Unlike a regular bit, which stayed firmly at 0 or 1, a qubit could exist in a blend of both states simultaneously until measurement forced a final result. This meant quantum systems could represent many possibilities at once. Instead of checking one path after another, they could hold multiple pathways together, dramatically expanding computational reach. The second principle was entanglement, one of physics' strangest discoveries. When qubits became entangled, their states connected deeply, even across great distances. A change in one could instantly affect another through quantum relationships that challenged classical intuition. Early scientists found this very disturbing, yet repeated experiments confirmed its reality. Entanglement allowed quantum systems to coordinate information in ways ordinary machines could never naturally reproduce. By combining superposition with entanglement across increasing numbers of qubits, quantum computers gained the theoretical ability to process extraordinary problem spaces simultaneously. For selected tasks, this was not merely an upgrade in speed, but a different category of computational power. Properly built quantum systems could transform cybersecurity, artificial intelligence, chemistry, military analysis, logistics, and advanced materials in ways classical systems could not easily match. This promise triggered one of the greatest technological races in modern history. Governments, universities, and corporations all pursued the same goal. Whoever mastered practical quantum computing could reshape global power structures. Google, IBM, Intel, and others pursued one path, while Microsoft chose something far riskier. Instead of following common designs, it committed itself to an unusual theory that many considered either brilliant or dangerously unrealistic. Microsoft's public image centered on software, productivity tools, and operating systems, yet behind that familiar reputation, it quietly invested in deep scientific research. In 2003, the company launched Station Q at the University of California, Santa Barbara. This initiative focused on a bold strategy. Unlike competitors, rather than refining standard qubits, Microsoft pursued topological quantum computing, a path rooted in abstract mathematics and unproven physics. The appeal came from quantum fragility. Conventional qubits were notoriously unstable. Heat, vibration, electromagnetic interference, and even tiny environmental disturbances could collapse delicate quantum states. This instability, known as decoherence, was the greatest obstacle in the field. Existing systems required extreme cooling and constant correction, yet errors remained common. Building large, useful machines under these conditions became painfully difficult. Topological qubits promised a possible escape from this weakness. Instead of storing information in fragile local states, they aimed to encode data in broader structural properties of a system. Because these topological properties depended on global arrangements rather than tiny disturbances, they were expected to resist noise naturally. In theory, this could produce qubits far more stable than conventional versions. This idea relied heavily on the work of mathematician Alexei Kitaev, whose theories suggested fault-resistant quantum systems might be possible. Microsoft embraced this vision aggressively. If successful, topological qubits could bypass years of engineering struggles faced by competitors. The company believed it was not simply improving quantum hardware, but potentially leapfrogging the entire race through a more durable foundation. At the center of this dream stood a mysterious particle concept called the Majorana fermion. First proposed in 1937 by Italian physicist Ettore Majorana, this particle possessed unusual theoretical properties that made it highly attractive for topological quantum systems. The challenge was severe because Majorana particles had never been definitively observed in nature. Microsoft's strategy depended on creating conditions where Majorana-like states could emerge artificially. This transformed Microsoft's mission into both engineering and discovery. For 17 years, the company poured enormous financial and intellectual resources into this pursuit. It hired elite physicists, built specialized research teams, and developed advanced facilities focused on condensed matter experiments. This was not a side project, but one of the most ambitious long-term bets in technology. By 2017, anticipation intensified as Microsoft signaled that major breakthroughs were approaching. After years of secrecy and scientific buildup, expectations grew around facilities, experiments, and evidence that topological systems were nearing practical reality. Now, the stage was set for one of the most unbelievable chapters in quantum research: the attempt to break through impossible physics. As Microsoft's quantum ambitions expanded, much of the visible work appeared to flow through research institutions, public grants, and academic alliances. Station Q remained the symbolic center, but the true machinery stretched far beyond one laboratory. University partnerships became essential because building topological systems required rare technical skills, custom materials, and nanotechnology so advanced that only a few places on Earth could realistically attempt it. Among those institutions, Delft University of Technology became one of the most important. Located in the Netherlands, Delft possessed extraordinary expertise in nanoscale engineering, semiconductor fabrication, and experimental condensed matter physics. Their researchers could design and manufacture delicate microscopic structures needed to test Majorana theories. For Microsoft, Delft offered not only scientific partnership, but also capability, turning abstract equations into physical devices measured atom by atom. This collaboration looked normal from the outside because large technology companies often work with universities. Yet around this specific program, observers began noticing patterns that felt different from normal academic culture. Standard university science often thrived on openness, publication, conferences, and broad peer discussion. Around parts of this project, however, were tighter layers of security. Access restrictions reportedly exceeded what many expected from physics departments. Silicon Valley operated on secrecy constantly, especially when billions of dollars and market leadership were at stake. Protecting intellectual property remained standard business behavior. Yet some observers noted distinctions between confidentiality and the broader pattern forming around this initiative. Non-disclosure agreements reportedly stretched wider than many researchers expected, and some findings seemed delayed from wider scientific examination longer than usual. Then came the publication that seemed to justify years of secrecy and ambition. In 2018, a paper involving researchers connected to Delft and Microsoft appeared in Nature, one of the world's most respected scientific journals. Publication there represented extraordinary validation. Nature's review standards were famously demanding, and acceptance often marked research as globally significant. This paper carried strong implications because it claimed strong evidence for Majorana fermions within nanoscale systems. For Microsoft's topological strategy, this was foundational. Majorana states were not a side detail, but a central pillar. If convincingly demonstrated, they could support the entire vision of stable topological qubits. Years of theoretical investment suddenly appeared to stand on experimental ground. For many, this looked like one of the most important moments in quantum research. But science did not end with publication. Independent replication remained essential. Other researchers began attempting to reproduce the findings using similar methods and conditions. This process was not hostile, but fundamental. Real breakthroughs had to survive outside the originating lab. Gradually, problems began to surface. Experimental outcomes elsewhere did not consistently match what the paper suggested should occur. Discrepancies triggered deeper attention. Scientists examining methods and reported data noticed irregularities. Questions emerged around measurement interpretation, signal processing, and how conclusions were framed. In theoretical and condensed matter circles, concern spread quietly at first. The issue was not immediate proof of fraud, but growing uncertainty around whether the celebrated conclusions truly reflected experimental reality. As scrutiny increased, investigators looked beyond polished publication figures toward raw underlying data. This step became crucial. Published graphs often represented processed forms of larger experimental sets, and scientific integrity depended on honest representation. Over time, examination revealed troubling issues. Some data treatment choices appeared selective in ways that strengthened the desired narrative while weakening contradictory signals. By 2021, after extended investigation, Nature formally retracted the paper. Scientific retractions were not automatically catastrophic because errors happened regularly in difficult research. Methods could fail. Interpretations could overreach. Honest mistakes were part of science's self-correcting structure. Yet this case felt heavier because the core problem involved not simple miscalculation, but selective presentation of evidence. The investigation found that certain raw data points inconsistent with stronger conclusions had been omitted or processed in ways that made results appear more definitive than they were. This distinction mattered greatly. The concern shifted from flawed interpretation toward whether experimental uncertainty had been shaped into persuasive certainty. Such actions struck at the heart of scientific trust. This development cast shadows over a program built on extreme expectations. For researchers at elite institutions, careers often depended on major discoveries. Publishing in top journals brought prestige, funding, and influence. Within a program carrying global technological stakes, pressure could intensify further. The race for quantum leadership was not merely academic. It involved market dominance, strategic advantage, and historical legacy. Such forces could create dangerous incentives around borderline results. As discussion widened, some scientists adjacent to the broader field began speaking more openly about internal culture, replication struggles, and the pressures surrounding frontier research. Their perspectives did not always imply coordinated deception, but they highlighted how extreme ambition, secrecy, and institutional expectation could distort judgment. Unfortunately, the line between hope and evidence had become dangerously fragile. The uncontrolled signals. The collapse of the celebrated paper did not trigger public confession or explosive headlines from inside the program. Instead, information moved through more discreet channels. Scientific conferences became places where side conversations carried unusual weight. Private correspondence circulated carefully. Journalists specializing in science began hearing fragments from people close enough to understand the pressure, but cautious enough to avoid direct confrontation. Through these scattered pieces, a more troubling portrait slowly formed. Behind the polished public image of innovation stood a research culture burdened by heavy expectations. Microsoft had spent years presenting topological quantum computing as a defining long-term strategy. Public presentations from executives had reinforced confidence, and investors had absorbed promises tied to future breakthroughs. The company's broader narrative increasingly treated topological qubits as a hidden advantage that could eventually outperform every competing system. Meanwhile, the conflict between scientific uncertainty and institutional expectation became increasingly difficult to ignore. Some departures from the program began attracting attention. They were not dramatic resignations surrounded by scandal. Instead, certain researchers gradually disappeared from visible association. Profiles changed. Affiliations shifted. In highly specialized scientific communities, these patterns often communicated more than public announcements ever could. Science journalists later gathered enough private accounts to suggest recurring themes. Several descriptions pointed toward an environment where disappointing outcomes were often treated less as final evidence and more as obstacles demanding reinterpretation. Negative data did not always end inquiry. Instead, pressure sometimes leaned toward adjusting conditions, refining analysis, or reshaping presentation until results better aligned with hoped-for milestones. That complexity became central to understanding what may actually have happened. The central mystery was not simply whether major claims had been overstated. Evidence strongly suggested that happened. The more interesting problem involved what the unfiltered experiments were actually revealing beneath the conclusions. If raw measurements contained persistent anomalies, then something physically real may still have been occurring, even if official interpretations stretched too far. By available accounts, Delft's devices were not producing random noise alone. Experimental systems generated measurable behaviors under carefully controlled conditions. These nanoscale structures operated near absolute zero, under intense magnetic precision, and within extraordinarily refined electrical environments. Such systems often pushed physics into unusual territory. When anomalies appeared, they demanded explanation. One major signal involved what physicists called a zero-bias peak. In conductance measurements, this feature had long been proposed as a potential indicator of Majorana behavior. If cleanly confirmed, it could support topological quantum theory. Yet the challenge was severe because zero-bias peaks were not exclusive to Majorana states. Conventional physical mechanisms could imitate similar signatures. This created a risky scientific gray zone. Researchers might observe data matching theoretical predictions on the surface, while alternative explanations remain equally plausible. Distinguishing genuine topological phenomena from ordinary quantum similarity required thoroughness. Cross-checking became essential. Independent tests, repeated validation, and near-perfect experimental discipline were necessary to avoid false conclusions. According to broader analysis, some Delft results likely fell into this uncertain category. Certain observations appeared suggestive enough to encourage excitement, but ambiguous enough to resist definitive classification. This ambiguity may have fueled the pressure to frame outcomes more strongly than warranted. A weakly understood signal, when attached to 17 years of investment, could become dangerously attractive. However, another layer made the situation even more complicated. Reports suggested that some device behaviors did not fit comfortably into either preferred Majorana explanations or established alternatives. Certain anomalies occupied stranger territory. They did not align neatly with textbook topological predictions, but they also resisted dismissal as simple artifacts or ordinary mimicry. This middle ground was scientifically fascinating. For theorists involved at high levels, this apparently created intellectual frustration. Experimental systems seemed to be showing something unusual, but available conceptual tools may not have been mature enough to describe it cleanly. Physics sometimes encountered precisely these moments, where observed behavior outpaced language and established models. Historically, such periods could lead either to breakthroughs or costly misinterpretation. In this context, the pressure to simplify became especially critical. Rather than presenting anomalies as uncertain but potentially important, institutional incentives may have favored packaging them within the more recognizable Majorana idea. The broader tragedy lay in how such a choice could distort both public understanding and scientific opportunity. If genuine anomalous phenomena existed, overstating them as solved could bury more interesting questions under reputational fallout. What emerged from this period was not a simple story of total fabrication or pure success. It was a far messier intersection of ambition, real experimental struggle, partial signals, theoretical limitation, and institutional pressure. Underneath flawed presentations, researchers may have been observing legitimate physical behaviors that challenged current frameworks without fully confirming the revolutionary outcome Microsoft most needed. And that was when things got out of hand. The missing years, reset, and silence. By 2023, Microsoft returned to the public stage with a far more cautious tone. After years of controversy, scrutiny, and damaged credibility, the company introduced a new claim centered on progress toward topological qubit. This time, the language was restrained. Instead of declarations about revolutionary proof, the announcement focused on reaching a defined engineering threshold involving measurement precision and reliability. The difference in presentation was immediately noticeable. Earlier ambition had leaned heavily on bold implications, while this newer approach appeared shaped by painful experience. Public wording became narrower, technical, and carefully limited. Independent verification was openly encouraged, signaling awareness that extraordinary claims now required extraordinary caution. Microsoft seemed determined not to repeat the catastrophic mistakes surrounding the earlier retracted paper. Yet even with this measured return, one major issue remained unresolved. The public learned what Microsoft claimed in 2023, but much less was explained about what happened between the collapse of its previous flagship evidence and this revised milestone. The missing years carried enormous significance because they represented more than scientific delay. They suggested internal problems. Between 2021 and 2023, many critical transitions appeared beneath the surface. Certain researchers had already left. Experimental paths once central to the program faded from visible prominence. Some facility structures and device configurations reportedly underwent dismantling, redesign, or replacement. Public-facing narratives emphasized continued progress, but they often did not fully account for how deeply earlier strategies had been revised. This period functioned less like steady advancement and more like reset. After the major retraction, the first generation of Microsoft's topological approach had lost much of its scientific standing. A company that had spent nearly 2 decades betting on one pathway now faced the reality that foundational parts of its strategy required re-evaluation. Resetting became unavoidable. During late 2021 and through 2022, certain branches of the Delft-centered effort were closed down. Although this did not mean Microsoft abandoned quantum computing altogether, the broader program survived, funding remained, and strategic ambition continued. However, specific research threads, device architectures, and collaborations appear to have been reduced or ended without major public disclosure. Official language described these changes through familiar corporate terms such as restructuring, refocusing, and strategic redirection. Such language contained some truth, because after scientific discrediting, any serious research institution would need reassessment. But restructuring alone did not fully explain deeper concerns about what disappeared alongside those closures. In standard scientific practice, even failed or inconclusive programs often leave behind preserved data, published analyses, or documented negative findings. Science advanced not only through success, but also through transparent dead ends. Null results prevented wasted repetition. Strange anomalies informed future theory. When research pathways closed, their records ideally entered broader scientific memory. In this case, some observers noted that portions of certain discontinued configurations did not appear to transition fully into public scientific literature. Not every pursued line produced visible closure through published finality. Some directions, active around early 2021, seemed to fade without comprehensive public accounting. This absence created uncertainty, especially given the extraordinary stakes surrounding the work. This pattern did not automatically prove conspiracy or malicious concealment. Scientific history contained many moments where institutions struggled with discoveries that did not fit existing framework. Researchers sometimes encountered observations too confusing, contradictory, or inconvenient to integrate easily. In such situations, data could be sidelined, not through evil intent, but through caution. Throughout scientific history, anomalous findings had often occupied dangerous ground. Clean success attracted celebration, while clear failure allowed criticism. Unexplained intermediate phenomena created problems. They challenged theory without validating replacement theory. They complicated funding narratives. They introduced uncertainty where institutions often preferred direction. Such situations could become especially vulnerable inside corporate or geopolitical races. Within Microsoft's quantum effort, this dynamic may have been particularly bad. If certain experimental systems revealed genuinely unusual physical behaviors that neither confirmed topological success nor fit ordinary explanations, institutional response could become strained. Publishing unresolved anomalies might preserve scientific honesty, yet it could also threaten investor confidence, strategic messaging, and unity. This tension transformed the shutdown period into something more complex than simple failure. Some interpretations suggested the institutional crisis emerged not just because nothing valuable was found, but because something real and scientifically intriguing may have appeared without fitting available models. Such situations could produce pressure, misrepresentation, and eventual reset when organizations lacked language or structure to manage them properly. Beyond Microsoft itself, this mattered because quantum computing existed within one of the highest-stakes technological competitions on Earth. This was not merely about prestige or academic curiosity. Quantum breakthroughs carried implications for cybersecurity, intelligence, economics, and global power. The pressure-shaping research culture came from far beyond one laboratory. Modern digital security depended heavily on encryption systems rooted in mathematical problems too difficult for classical computers to solve efficiently. Banking systems, government secrets, military communication, and private data all relied on this foundation. A sufficiently powerful quantum machine could theoretically dismantle many current encryption systems by solving these problems faster. Such capability would transform strategic power immediately. Encrypted archives captured today could become readable tomorrow. Governments understood this clearly, and it intensified pressure across every major technological power. Around the world, governments, corporations, and military planners recognized the same reality. Whoever reached practical quantum advantage first could reshape the balance of digital power. The race for transformative breakthroughs created incentives not only to produce results, but to frame them competitively. Funding, prestige, and national significance could distort judgment. Under such pressure, anomalous findings often became liabilities rather than opportunities. In a field where the unknown might hold the greatest discoveries, institutional pressure increasingly risked shaping not only what science revealed, but which parts of reality were made visible. So, what has been the truth behind all this? The discovery buried beneath the failure. Beneath the public collapse, failed LPL headlines, and damaged credibility, another possibility lingered quietly beneath the surface. The deeper significance of Delft may not have been that researchers completely failed, nor that they secretly succeeded exactly as planned. A more complicated possibility emerged through the fragments left behind. Their experiments may have been brushing imperfectly against a real but poorly understood layer of quantum behavior. Topological quantum theory often appeared beautifully clean on paper. Mathematical models described elegant protection mechanisms where quantum states gained resilience through structural properties rather than fragile local conditions. In theory, this offered a path toward stable qubits, yet real physical systems rarely behaved with mathematical purity. Materials contained imperfections, devices introduced noise, and environmental conditions created interactions theory often simplified. This gap between theory and physical reality may have become one of Delft's most important hidden lessons. Rather than discovering textbook-perfect topological states, researchers may have encountered transitional zones where conventional quantum effect and topological behaviors blended in unstable, unfamiliar ways. Such a regime would not fit the simple predictions investors wanted or the clean breakthroughs headlines demanded. If this interpretation held weight, then the most scientifically valuable outcomes from Microsoft's long investment were not necessarily the announcements or strategic presentations. The truly important findings may have been the anomalies that resisted explanation. Those strange, unresolved signals may have carried deeper information than the overstated claims that later collapsed under scrutiny. Microsoft did not remain entirely silent after the controversy. The company publicly acknowledged the paper's retraction. It restructured key parts of its program and continued publishing newer work with more disciplined caution. Recent efforts appeared technically serious and more carefully documented. Yet, within all this controlled communication, certain absences remained striking. Several important questions never received satisfying public clarity. The fate of raw data from some dismantled experimental paths is still unknown. Specific researchers who quietly exited during critical years largely avoided detailed public reflection on that period. In scientific culture, people often moved on from failed projects openly, especially when failure itself offered lessons. Here, however, parts of the silence felt narrower, more deliberate, and shaped by something beyond ordinary disappointment. The absence was not total, but selective. Some former participants remained active in adjacent physics disciplines. Their later work suggested continuity with theoretical puzzles explored during the Delft era. This continuity implied that core scientific questions did not disappear when the institutional structure changed. Rather, interest persisted and inquiry continued. Yet, direct engagement with the deeper unresolved details of that specific chapter often remained limited. A careful interpretation of available evidence pointed toward a more restrained conclusion than public hype once promised. Microsoft likely did not build a fully realized topological quantum computer during those years. The retraction and broader scientific response strongly weakened such claims. But this did not mean nothing meaningful emerged. A more plausible outcome involved discovering that the boundary between ordinary quantum effects and topological protection in practical materials was far less neat than elegant theory predicted. Real systems may have revealed a messy landscape where behavior depended heavily on material design, fabrication precision, environmental controls, and subtle interactions not fully captured by dominant models. This would have been less sensational than proving Majorana particles decisively, yet potentially more useful. Honest publication of anomalous intermediate findings could have forced the broader field to revise assumptions earlier. It could have reshaped understanding of practical barriers and redirected global research more effectively. Scientific progress often depended less on dramatic victory than on accurate maps of complexity. Instead, institutional pressure appeared to favor a cleaner story. Once the chosen narrative collapsed, trust in surrounding data suffered as well. Under such conditions, something genuinely interesting but narratively inconvenient could become mishandled. Instead of entering public science as a difficult puzzle, it might become overstated, then discredited, then partially abandoned. The troubling part was not necessarily evil intent, but inability to process complexity honestly. Somewhere within servers, archived systems, internal datasets, or forgotten experimental records, unresolved pieces of that period may still exist. Whether they represent profound new physics or merely difficult engineering artifacts remains uncertain. Yet, the possibility that real anomalies were encountered and inadequately integrated remained one of the most compelling dimensions of the entire story. Meanwhile, the global quantum race continued. Microsoft remained a participant, now more cautious. Competitors advanced through different architectures. Governments maintained pressure while encryption, intelligence, and economic stakes kept rising. But beneath every polished announcement lingered the same deeper reality. Nature itself did not adjust to corporate messaging. Physical truth operated independently of investor timelines, strategic turns, or damaged reputations. If Delft's strange signals reflected genuine aspects of quantum systems not yet properly understood, those behaviors would not vanish because one program mishandled them. Physics could be delayed, misunderstood, or buried institutionally, but not erased. Eventually, similar materials, similar temperatures, similar nanoscale structures, or entirely different experiments elsewhere may encounter comparable anomalies again. Another laboratory, perhaps under different incentives, may observe what Delft struggled to define. If that happens, history may reinterpret Microsoft's troubled chapter less as simple failure and more as an early, flawed encounter with a phenomenon science was not yet prepared to explain clearly. Beneath all of it, the deeper behavior of quantum matter remains unchanged, still waiting inside the structure of reality itself, ready to surface again whenever experimental conditions align closely enough for someone else to notice what was there all along. If you enjoyed this video, like and subscribe, and also click the next video shown on your screen.